If I take the derivative of negative 412, it's still just a number. What's the derivative of a number? Yes. If I take the derivative of 47.38, it's a decimal. It's okay. It's still a number. My derivative is 0. When I take the derivative of 3t plus 5 with respect to t, by the way, just kind of practicing notation here, I know that anytime the function is written like this with some sort of variable and then another variable in parentheses, that's telling me that that variable in parentheses is the thing that's acting like X, for lack of a better word, right? We call this our independent variable. And n is our dependent variable because n depends on the value of t. So here, when I take the derivative of a constant times t, I just get the constant. And when I take the derivative of 5, that's equal to 0. We don't have to write the 0 in this case, but I am just sort of for completeness writing that 0. No, what goes under there? Sorry. This is a super common one where, especially after you've seen the quotient rule, I see students start to try to use the quotient rule on this. Pause for a second. Is there a way for us to rewrite this to say a number times x? And there is. This is the same as 1/4 times x. So when I take that derivative, I've got a constant times x, and that derivative is just the constant itself. Looking at the derivative of 1 minus 4x, I'm just going to take that as two separate pieces. So the derivative of 1, I get 0. And the derivative of negative 4x, that negative 4 is the constant times x. I'm just going to get the constant back. Some of you in web work have had problems that include some sort of constant that's being, so it looks like there are 2 variables in the problem or 3 variables in the problem, but actually there's only one variable. And then the other thing sometimes we call parameters, because they're numbers that we haven't been told what their values are, but we're supposed to treat them like a constant. Notation wise, I would read this as K of S, which means S is the thing that's acting like X. And if R is a constant, then I have a constant times my variable, and the derivative is just the constant. I do want to pause here to give everyone a second to think about this. Why does it make sense intuitively or graphically that the derivative of y equals 3x minus 8 is equal to 3? Someone added in the chat in Canvas kind of the more graphical thing, which is the derivative is giving us the slope of the tangent line. So if we were in like an algebra 2 class and I just looked at that equation and said, hey, what's the slope? The slope of that line is 3. So it makes sense that those two things should work out. That if the derivative is calculating the slope, and we already know how to find the slope of this, they should match up. Okay. The next sort of derivative rule that we need to memorize is the power rule. And it looks kind of gross written like this, but I promise if you do enough problems, you won't be thinking about it in terms of a formula. You'll just start to do it intuitively. Now, the reason that I've also added the general power rule here is, and really that general power rule comes from the chain rule. But if I have something in parentheses raised to an exponent, then what that general power rule says is take the stuff that's in parentheses and bring the exponent down, subtract 1 from the exponent. But the extra piece we have to do is to multiply by the derivative of what was in parentheses. So let's get some practice with that. In terms of that general power rule, this says, I know it's gross notation, but take that exponent. If it's a constant, right, I'm going to take that power, multiply it by the coefficient in front. So I'd have 3 times 4, I'd get 12, and then subtract 1 from the exponent. I'd take the 2 times the -5 and get -10, and then subtract 1 from the exponent. My suggestion is when it comes to these last two pieces, the 3x minus 6, don't think of those as a power rule. Really go back to, it's worth it to memorize a constant times x, the derivative is the constant. So if I'm looking at 3x, I know that derivative is 3. And the derivative of a constant all by itself is 0. Again, I don't have to write the 0, it's just a choice. I'm going to give everybody a couple minutes to just quickly try these on your own. Also, just in terms of, like, you don't necessarily need to memorize this part, but I do think that it's helpful. I do think that it's helpful with the fractions to kind of start associating things. So the more that you can memorize some little things, the more you kind of free up your brain space to invest time thinking. So when I look at this, just as a kind of note to self, 1/2 minus 1 is -1/2. And 1/3 minus 1 is -2/3. And both of those show up quite a bit because anytime I'm looking at a square root of x or a cube root of x, and I have to take the derivative, I'm going to end up doing that fraction math. So if you kind of just add those as tiny things to memorize, it could be helpful. Okay, I'm going to get rolling on this. And I do see that there's a question in the chat, and I'm totally going to address it in a second. So I've got a -2 in the exponent. I'm going to bring that down in front and subtract 1 from the exponent. So when I subtract 1 from the exponent, -2 minus 1 is -3. For my next part, I've got 3 times 1/2 when I bring the 1/2 down, and I'm going to write that as 3/2. And when we subtract 1 from the exponent, that's -1/2. 10 times 4 is going to give me 40 t to the 9th. If I come over here, derivative of 1 is 0. You don't have to write the 0. I'm doing it for completeness. The derivative of a constant times x is just that constant. And then for this one, I'll have 3 times 5, which is 15x squared. So on this next one, r is a constant. So when I take the derivative of r times s squared, if I think about what we did with the 5 times x squared, right, we ended up with the 2 times 5 and then just an x to the first. So this is going to look like 2 times r s. If r is a constant, 3 times a constant is still just a number. And if 3 times a constant is still just a number, then that derivative is 0. My s to the 9th is going to look like 9s to the 8th. Here, I do have parentheses, and I've got some stuff in parentheses raised to the 5th power. So this is really a general power rule because I've got some stuff to a power. And when I take that derivative, The first piece of it is to just treat it like I would any other power rule problem. I've got some stuff to the 5th, so I get 5 times the stuff to the 4th. But then the chain rule piece is now I need to multiply by the derivative of what was inside. And what was inside, I've got 3x to the 4th. So another power rule, bring my 4 down, multiply by 3, x to the 3rd, derivative of 6 is 0. I'm not going to write the 0 this time. I'm just going to leave it like that. I've also been getting a lot of questions about whether you need to simplify these. For sure, if this was a web work problem, I would just type that in. There really isn't a need to simplify. This is pretty simplified. If you think about back to like an Algebra 2, Math 3 kind of class, oftentimes getting something in its factored form was the simplification we're looking for. So here it's kind of already in the factored form. I would just walk away. This next one is an example of there isn't anything written in parentheses explicitly right now, but I am going to have to use chain rule or the general power rule. So here, the first thing that I have to do is to rewrite that radical. So when I look at this, I'm going to rewrite that problem to say I've got t squared plus 3t. I need to write in the parentheses raised to the 1/2 power. So I'll give you a minute to finish that one up. You ready for this derivative? So I've got stuff in parentheses raised to the 1/2 power. So thinking about that general power rule, I'll bring down my 1/2, have the t squared plus 3t, subtract 1 from the exponent, and then that chain rule piece or the general power rule piece is that I need to multiply by the derivative of what's inside. And when I multiply by what's inside, derivative of t squared, I'll bring that 2 down. This is t to the 1st power. I don't write the 1 there because it kind of starts to look like the notation of a derivative. So I'm just going to leave that as 2t. Derivative of a constant times t is the constant. There are ways to rewrite this if you really, really wanted to. For sure, if I was typing this into WebWork, this is my best option of how to look at it to type this into WebWork. Alternative ways to write this, and especially if you were like trying to do a book problem and check your answer in the back of the book, this is equivalent to me writing 2t plus 3 in the numerator. Because of that negative in the exponent, I know that means this whole piece could go into the denominator, and a 1/2 power means I could write that back as a square root. So another way that you could write this is like that, but it's not actually more simplified, right? So this is actually, I would argue, the most simplified way to write it. This is just an alternative equivalent way to write it. And I feel like our textbook often rewrites radicals after they finish the problem, which always seems kind of silly to me because the first step before you take the derivative is that you have to put it into fraction exponents, and then the book does the opposite when they finish. Next one up here is an example where I would rewrite this before doing the problem. So I've got a constant on the top, and basically all the action is in the denominator. We might think about using the quotient rule, but I think it's easier because there's just a constant on top to rewrite this to actually be 1 minus 4x minus 5x cubed, whole thing to the -2 power. Because now I can apply the general power rule to this. So my general power rule looks like bring that power down in front, subtract 1 from the exponent, and -2 minus 1 is -3, and then multiply by the derivative of the inside. And on the inside, derivative of 1, since it's a constant, is 0. Derivative of -4x, constant times x is just going to become the constant. This one I have to actually do a power rule on. So 3 times -5 is going to give me -15 x squared. In the spirit of, do I think you should simplify that? I think it is simplified. If you wanted to rewrite it in an equivalent form, you could. And that equivalent form might look like, since I've got a negative exponent, I could choose to put this part back down in the denominator. And in the numerator, I could choose to distribute through the -2. So if I were to take that -2 and distribute it in to the other parts that are in the numerator, this could look like -2 times -4 would be a +8. -2 times -15x squared would be a +30x squared. To continue in the spirit of having fun with messing around with constants, I will give you a minute to do this one and just be careful. R is a constant. Just to make sure I get this in our notes for today. R is a constant. So if I had S to some gross power, doesn't matter what it is, if it's a number, I bring that number out in front and I have S to the number -1, which means we kind of just have to give this a placeholder and say, I don't know what R is, but it's a number. So I'm going to bring it down in front and then subtract 1 from the exponent. Next piece feels a little more comfortable because the R is just a constant and sitting out in front. So this one feels a little more comfortable. 7 times 3, I'm going to have 21R S to the 6th. And then if R is a constant, even if I square it, it's still just a number. And the derivative of a number is 0. The derivative of e to the x is e to the x. The derivative of an exponential when the base is not e looks like the natural log of the base times the base raised to the x power. You just have to memorize them. Product and quotient rule, you also just have to memorize. Now, on the product rule, because we've got multiplication, which the fancy math term is that multiplication is commutative and addition is also commutative, which means you can do it in either order. This is not the only option for how we write the product rule. I just like to keep it in the same order as quotient rule. I have a typo on the page. Someone find my typo. I just realized. Dun, dun, dun. This should be a minus sign in my quotient rule. Oops.
Oh, yeah.
Yeah, so I will fix that. In fact, I'm gonna fix it on my worksheet, like my actual copy of the worksheet right now, my file for the worksheet, because otherwise I'll forget to go back and do it later. It's been fixed on my worksheet and cool. Okay, so sorry about that, folks. I will upload a new PDF sometime later today. Okay, so product and quotient rule and these exponential rules, we just have to get them memorized. But I do think that the more practice you do with them, it will kind of memorize itself, but sometimes you might have to do 20 or 30 problems to get to that memorized state. So let's do a couple together here. First of all, how do I know that this is a product rule? It technically doesn't have to be a product rule. You could choose to FOIL this out. And when I say FOIL, I just mean to multiply all of the parts out. That's an option. I'm going to go ahead and practice with the product rule, but it is an option to multiply everything else out first. So I know that my product rule has to look like the derivative of the first part times the second part left alone, plus the first part left alone times the derivative of the second part. And I usually like to just give myself parentheses to start off with so that I know where my pieces are going. So if I take the derivative of 3x squared plus 5x, that derivative of 3x squared looks like 6x plus a 5. And then I leave the second piece alone. Plus, I leave the first piece alone and take the derivative of the second piece. And since the derivative of that second piece, I'd bring my 4 down, subtract 1 from the exponent, and I could write a -0, but I'm not going to. Now, if you're about to ask me, do we simplify that? It is simplified already. There isn't something you can do to make it look better. You could do a whole lot of extra work multiplying all of that out. But don't, please. Just walk away. On this second problem, because there is a monomial on the bottom, meaning there's just one piece on the bottom, you have the choice that you could rewrite this as 2 separate fractions, simplify using exponent rules, and then take the derivative. Or you can just use quotient rule. I don't particularly care. How would you like to do the problem? I'll let you decide. You can try the problem on your own, and I'll let you decide whether you want to rewrite it first or practice with quotient rule. Yeah, so the question is, could you leave it like this on an exam? Absolutely, you can leave it like this on an exam. You shouldn't, no one wants you to waste the time multiplying things out. I will say there is kind of an exception to that in the case of if you were asked to find the derivative at a particular value of x, you should plug that x value in. And if the arithmetic is reasonable, you should do it, right? So that is a good question. Like, yes, on an exam, I would leave it there. But let's say we were actually asked to find dy dx at x equals 0. If I was asked to do that, and so I got my y prime, and then I was plugging in 0 everywhere, 6 times 0 plus 5 times 0 to the 4th minus 2 plus 3 times 0 squared plus 5 times 0 times 4 times 0 cubed. You probably would lose points if you didn't simplify that. Because now I'm down to like numbers that are very reasonable to work with. So 6 times 0 is 0. This really becomes 5 times -2. This whole thing is 0 because I'm multiplied by 0 at the back. So that would be -10. And on a test, if I was asking for this at a particular point, I would expect you to clean that up to be -10. The other exception might be if what you got after taking the derivative for that product rule had common factors that you could factor out. Let's do it with quotient rule. And if I'm going to do it with quotient rule, I think about the whole top as being sort of my f function and the whole bottom as being my g function. And if I go ahead and get parentheses, I'll have a couple of pieces with subtraction between them. Sorry about the typo. And then I'll have something squared on the bottom. In terms of that formula, what goes on the bottom is whatever was already in the denominator. So I'm going to have x cubed, and that's the thing that's getting squared. In my numerator, if I take the derivative of the top, I'll have 5x squared minus, sorry, I said the derivative. And then I didn't take the derivative. So my derivative is looking like 10x minus 8. And then I'll leave the bottom alone. And I'll leave the top alone and take the derivative of the bottom. And the derivative of x cubed is 3x squared. Now, this is a case where if you have the time, we probably should simplify this. How do I know that this one I should simplify and the other one I shouldn't simplify? When I look at my numerator, there's something that I can factor out. And as a general rule, the factored form is our more simplified form. The other clue that I can do at least one more step to simplify is I've got a monomial raised to a power, and powers raised to power means that I could multiply that. So I should for sure clean up the bottom. And if I wanted to simplify, I can factor on the top. So let's do those two steps. Yeah, I'll write it down here. So in my denominator, x cubed squared would be x to the 6th. In my numerator, I've got two pieces that are separated by that minus sign. And I'm looking at the x cubed and the 3x squared, and I notice I can factor out an x squared. So if I were to pull out an x squared, then from this piece, I would still have the 10x minus 8. And since I've pulled out an x squared from the x cubed, I'd have an x left. From the second piece, I've pulled out the x squared, so I still have a 3, and then the 5x squared minus 8x. Just as a general note about simplifying things, on an actual exam, I would wait to simplify until I had felt like I had tried all of the problems. Because in general, you'll lose fewer points from simplifying than if you just didn't start another problem at all, right? So that would be where I would put my attention. But then if I had extra time to go back and simplify, we can keep simplifying here if we want to. So the x squared over x to the 6th means that I can cancel 2 of those x's out and be left with x to the 4th on the bottom. And then here in the numerator, these are both pretty easy to multiply out. So I could 10x times x would give me 10x squared, and then minus an 8x. And over here, I can distribute that -3 out. So if I distribute the -3, that's -15x squared. 3 times 8 is 24. Minus a minus will make that a plus 24x. And you'll notice we now could combine like terms in the numerator and take one additional step to simplify that if you wanted to. So the derivative of e to the x is just e to the x. And then product rule, my next part, I leave the second piece alone. And then I leave the first piece alone and multiply by the derivative of the second piece. So 2x minus 3x squared. If you are thinking, hey, should I simplify that? If you're typing it into WebWork, you definitely don't need to. You can just type that whole thing in. If you are thinking, should I simplify this? Again, take the time to make sure you've tried every other problem before you think about coming back to simplify. But the question you should ask yourself to decide if you can simplify something is, can I factor it? Is there something that my terms have in common that I'm going to be able to factor out? For sure, I can factor out an e to the x. And I think we can factor out an e to the x and an x, but I don't think I can take an x squared out of this one. I would do it in 2 steps just because I have a hard time like visually doing them at the same time. If you are able to take out the e to the x and the x all in one step, totally. I'm just going to take the e to the x out first. And then I'd have x squared minus x cubed plus 2x minus 3x squared. And now I'll go ahead and take my x out. So I'd have x times e to the x. I'm going to go ahead and combine like terms when I do this also, because I see an x squared and a negative 3x squared. And if I put those together, I'd have negative 2x squared. So I'm pulling an x out. So I'm going to have negative x squared from the x cubed part, negative 2x from the negative 2x squared, and then plus a 2. And take the derivative of something where the base is not e, but it's a number to the x. I know that's an exponential because my variable is in the exponent and I have a number down in the base. So when I take this derivative, our derivative rule is to take the natural log of the number that's in the base and then multiply by the exponential. Next up, I've got a quotient rule for us. That's all I have to do. That's all we have to do. Yeah, there's nothing additional to do to that 5 to the x. That's it. We're just going to memorize that derivative rule. Yeah. And just like fun fact, if I had had e to the x and I treated it the same way, that would look like natural log of e times e to the x. But what is the natural log of E? What's that value? Yeah, it's 1. So the formula works even for e to the x. I'm going to go ahead and get my derivative going here. So for the quotient rule, I'm going to take the derivative of the top. And the derivative of x squared plus 1 is going to give me a 2x. Multiply by leaving the bottom alone. I'm going to subtract, leave the top alone, times the derivative of the bottom. And the derivative of e to the x is e to the x. So this is definitely a place where we can simplify. So maybe we should simplify. Again, I'm going to look at that and think, is there anything I can factor out? And in the numerator, I can factor out the e to the x. And if I pull out e to the x, I'm looking at 2x. I'm going to go ahead and distribute that minus sign through. So I'd have 2x minus x squared minus 1. Now, this is actually something that comes up a lot, both in 17a and 17b. It's really nice to be able to have different ways to think about e to the x squared. So if I use, all of these are like equivalent forms, but look different. So e to the x squared is the same thing as e to the x times e to the x. But I can also use exponent rules to say, if I've got a power raised to a power, that means I multiply those. And that's e to the 2x. And just, this is nice to kind of have in your toolkit as 3 different ways to think about this, because the different versions are helpful at different times. Right in this moment, I would like to think about that e to the x squared as e to the x times e to the x, because that's going to let me cancel one of those out. So that's kind of the version that I would rather have in that moment. So I could write that as negative x squared plus 2x minus 1 all over e to the x. And I've just got one last question that I wrote on our worksheet today. And again, I'm throwing letters at you. K is a non-zero constant. I got asked the other day in office hours, like why sometimes in web work it tells you that the constants are positive or non-negative, and there is no reason except K can't be 0 or the whole problem would be undefined. And if the whole problem is undefined, then I could be really lazy and say the derivative is not defined because the whole function might not be defined because K could possibly be 0. So in those web work problems or the textbook problems where they're telling you something about the constant, it's usually just to make sure that your domain makes sense. So couple of options here. It sure looks like a product rule because I got 2 things multiplied together. Also, there's a monomial out front. So I could multiply the k e to the x in. I call that a monomial. It's not, that's not a power, it's an exponential, but I just have one term out in front. And so I could distribute that in first. I'm going to go product rule because it's kind of the theme of what I was trying to practice today. Let's just do this one together. So K is a positive constant. T is the thing I'm taking the derivative of. If I'm going to do a product rule, I'm going to go ahead and get myself my pieces here. So if I take the derivative of k times e to the x, k is a constant. That derivative is k e to the t. I'm going to leave that second piece alone, the t squared minus 1 over k. I'm going to leave the first piece alone and then take the derivative of the second piece. K is a constant. When I take the derivative of t squared, I get 2t. Since k is a constant, 1 over a number is still a number. And when I take that derivative, it would be 0. Let's say that my entire function was, let's go with 8 times e to the t. So this one's actually like, I'm going to do this as if it were a product rule. So if I think about that as a product rule, 8 times e to the t, the derivative of 8, because it's a number, is 0. So I'd have 0 times e to the t plus 8 times e to the t. And 0 times some stuff is 0. Now, if I had 5x to the third, I'm guessing you wouldn't treat that as a product rule. You could. And if I did treat that as a product rule, I would end up with the derivative of 5 is 0 times x cubed plus leave the 5 alone times the derivative of the x cubed. And that first part would go to 0. So anytime I have a constant times a function, I like to say the constant is just coming along for the ride. Okay, I'm going to have x squared minus 3xy plus y squared is equal to 10. This is the equation of an ellipse. It's kind of a slanted ellipse. I'm not expecting anyone to know what that looks like, but it's some kind of like tilted ellipse thing. I'm not sure if it's tilted that way or the other way. It's some kind of tilted ellipse thing. And what I would like to do is to find dy dx. So in terms of implicit differentiation, this is telling me that wherever I see a y, I should treat that like it's a function, but we don't know what the function is yet. And whenever I see an x, the derivative of x is equal to 1. So if I go through this and I've got x squared, I'm going to give myself a little bit of space, minus 3xy plus y squared is equal to 10. There is no easy way to make that say y equals. That's really how I know it's going to be an implicit differentiation problem. Since there's no way to make that say y equals, I'm just going to take the derivative of each piece. So when I take the derivative of x squared, I get 2x. Now here, I have two things multiplied together. I've got the 3x and the y. By the way, this notation at the beginning is telling me that both x and y are variables. Neither of them should I be treating like a constant. So it's not like some of the other problems that I made us do just now. Both of these are supposed to be variables. So when I take the derivative of 3x times y as a product rule, I'm going to kind of group that 3x together and then look at the y. So my derivative of 3x, it's a constant times x, so the derivative is the constant. And then I leave the y alone. Plus, I leave the 3x alone, and I take the derivative of y. Well, two different notations, either one is fine. I'm going to write this as when I take the derivative of a y, that I get dy dx. You could also just write y prime, whichever you're more comfortable with. My handwriting gets a little messy, so I always worry about just writing a prime in there, and that's starting to look like a 1. So I like to actually write the dy dx. When I take the derivative of y squared, even though there are no parentheses there, I want to think about that as a general power rule. I've got some function, we're calling it y, and it's squared. So when I take that derivative, I'll get 2 times y times, if that were in parentheses, I'd have to multiply by the derivative. And I'm going to multiply by dy dx, because I don't really know what that function y is. And if I take the derivative of 10, which is a constant, I get 0. That's it for the taking the derivative part. The rest of it is algebra. So next step, algebra-wise, is that I need to get the dy dx by itself. And the way I'm going to do that, I'm going to distribute everything out. So I've got 2x minus 3y minus 3x dy dx plus 2y dy dx is equal to 0. And then I want to get all of my dy dx parts on one side of the equation and everything else to the other side. So I'm going to subtract 2x. I'm going to add 3y. And then from these parts that are left, I'm going to factor out the dy dx. I know I kind of did 2 steps at once there. And now I'll just divide by this whole mess and have dy dx is equal to negative 2x plus 3y all over negative 3x plus 2y. Sometimes on the implicit differentiation problems, you might be asked to find the derivative at a particular point. Here, I didn't ask us to do that, but if you were given a point, then you would plug in both the x value and the y value, kind of where they are in the equation.